بسم الله الرحمن الرحيم. الله يعطيكم العافية. في محاضرتنا الرابعة من شابتر 4. اليوم راح نحكي عن البلوك كودينج. أنا في سلايدز 37. We talk about block coding. Let's explain what we mean by block coding. Block, it means a group of data, M bits. We usually receive M group of bits as input streams. We divide the bit streams into groups. Each group is one bit, M bits. For example, 4 bits. Then we find or we substitute these M bits into N bits. So every M bits from the input stream is substituted with N bits as a new code. So it's just like adding a new bits in it. Usually N is larger than M. For example, 4B, 5B, which means every 4 bits is substituted with 5 bits. So so the block coding is normally normally referred to as M bit in bits. So we replace each M bits a group with N bit groups. Let's explain more in details what we do. First, the division step. The step in this case, the bit stream is divided into group of M bits. Let's say, for example, the M bit M is here 4. Yeah. Let's assume here we have M bit M equals 4. Then we substitute every M bit groups are substituted with N bits, and N must be greater than M. For example, N is 5 and M is 4, okay, for example. Now we choose the N bit in a way that we need to have synchronization, or in other words, we need to have clocking in the signal. Then what we do, the N bit groups are combined together to form the new bit stream. So we receive M bit streams, and we the output of this encoder is a new N bit stream. Then we feed the new N bits to what we call line encoding. For example, we might use non-return to 0, we might use Manchester or whatever. Okay. Here we can explain more. Here what we have M bits. This is the stream of data coming from the computer, for example, from the mobile, for example. So now we divide the input stream to M bits. M here, let's say maybe here 8-bit, 8-bit, 8-bit. Then for each 8-bit or for each M bits, we find N bits which is larger than M bit. For each block, we find a new block of data which is larger than the original one. Okay, and then we combine the N bits and we send now these bits, which means every code has a new code or a different code to be sent after that. Let's take an example. Let's take the 5B, 4B, 5B. 4B, 5B means every 4 bits are substituted with 5 bits. We take every 5-bit block of data, and then we find 5-bit codes. These codes are line encoded with, for example, non-return to 0. This is, we took non-return to 0 inversion, if you remember. Here, in this example, which has been used, I believe, in token ring network, each code has no more than 1 leading zeros, which means that the 0 from the beginning 0 bit should have only 1 0, and no more than 2 trailing zeros. في آخر الكود اللي بنحكي عن الان كود الآن مش لازم يكون في أكثر من 2 zeros. بمعنى آخر هون we are trying to minimize the consecutive zeros. Okay, i.e. no more than 3 consecutive zeros will ever be transmitted. ما راح نلاقي بأي كود نرسله من الان بت ما راح نلاقي 0 0 0 ورا بعض. اوكي، طيب بالنسبه للونز، طيب ليش هل راح نلاقي 1 1 1؟ ممكن نلاقي 4 ونز، ممكن نلاقي 5 1. طيب ليش؟ لانه احنا بنحكي عن run return to 0 inversion. الانفيرجن يعني at 1 at mark we invert, which means we have synchronization. Okay, so we'll try to the aim of the code here is to impose or to have codes that has more ones in it. Here, since we are substituting every 4 bits with 5 bits, which means we add like a 20% extra data. This is what we call stuffing. Extra data is 20%. Why 20%? Because from out of 5 bits, we have 1 bit is redundant or an extra bit. In this case, the baud rate or signal rate would be increased by 20%. طيب بما انه الان اكبر من الام ف 2 to the power m مثلا 2 to the power 4 هون 2 to the power 4 16. فwe have 16 possible patterns. الاوتبوت 2 to the power 5 اللي هو 32. طيب احنا راح نستخدم فقط 16 out of 32. طيب شو بنعمل بال 16 الاكسترا 1؟ اوكي، we use them for error checking, for controlling, for control signals and something else. The DC component one will be minimized as there will be DC component because non-return to 0 inversion has DC component, but since we are having more ones in the chosen code, the output code, that means the DC component will be minimized. Okay. And then another example, 10B, 8B, 10B. 8B, 10B means 8B, 8-bit, every 8-bit, we choose another code with 10 bits in this case. Okay, this is the same as this one, but in this case the code is the different encoding scheme with higher data rate support. Okay, let's explain the idea here. Here the encoder. We have here a stream of data coming, 1 zeros, 1 zeros, or whatever. We take in the 4B, 5B, every 4 bits, we take every 4 bit as a group, we substitute it to 5 bits, okay? And then we feed this to non-return to 0 inversion. Then we have the digital signal as an output for the encoder. It goes to the receiver via the link, and there is a decoder here that will convert the non-return to 0 back to the original data which was sent here. Here, that means we need to have a lookup table. From where we're going to look at the table? The lookup table would be will be stored in the buffer here or in the encoder itself. Okay. Here and we explain more. Here, this data we are having, for example, and we want to send originally. So we divided the original data to 4-bit block. This is one block, another block, third block. For example, this block is transferred to 5 bits. And you see here the other code, the new code, has more ones and one zero at the end. For this code, we choose this code, has more ones, this zeros. And this one also is transferred to a code with five bits as an output and so on. So here the code we are sending, the 5-bit blocks we are sending and feeding to non-return to 0. Okay. The lookup table looks very much like this. As we said, this is for the data we are receiving. If we receive now, if we have a block here, the block here, if it is 000, from the table, the encoder will choose this code. So every time you have a block with 000 originally, it will be substituted with 5-bit code, which will be this code. If we have 001, so this is what I said, it's 2 to the power 4. 2 to the power 4, which means we have 1, 2, 3, up to 16 codes from 000 to 1111. Okay? We have 16 possible codes. Now, each code is substituted with using this table with a code from this column. Okay, so always, for example, if we have always 111 to send, the code will be sent this one, which is 11101, 5 bits. So we have here extra bit. For control signal, so sometimes we want to halt, so we can send this code, which is not the encoded sequence. Okay, this is out of the 32 codes. We said 2 to the power 5, since n is 5. 2 to the power 5 is 32. 16 of them is used for the input data, and the rest we can use them for control data. For example, we want to reset, we send this code. We want to quit the session, we can send this code, and so on. See, these are for. Still, we have used around 1, 2, 3, 4, 5, 6, 7, 8 codes. We have 8 codes are unused out of the 32 here. Okay, let's go to let's take this example. If you understand the concept, so the concept is having block of data m bit, and the previous example was 4 bits. Then we choose the best the best code that will impose or minimize the DC component, the baseline wandering, and so on. This example wants us to calculate the required bandwidth. We have a system. We send the data with a rate 1 meg. That's n. That is the data rate, which is n. Okay. So n here is 1 megabit per second. What is the minimum required bandwidth using a combination of 4B, 5B? If we use 4B, 5B, the one we just explained, and we use it with non-return to 0, or we use it with Manchester. What is the bandwidth if we use Manchester? What is the required bandwidth if we use non-return to 0 inversion? Okay, for 4B, 5B, n is 1 meg. Since for every 4 bits we use 5 bits, that means we have 1 bit extra, which is 20% as redundant bit, extra bits. Okay, so that would also, the bit rate is increased. So we are not sending now 1 megabit per second. Now we're using what we need. The bit rate is increased to also 20%. So it is 125. 125. I believe it is 120. It should be as 20%. The minimum bandwidth here for non-retain to zero, if you remember from the table and we calculated, is n over 2. For Manchester, it is n. Okay? So n here is 125 or 120 over 2, which is half of it, which is 625 kilohertz. That is the bandwidth. If we use non-retain to zero, but if we use Manchester, then we need n, not n over 2, which is twice the bandwidth of the non-retain zero. And here the bandwidth would be 1 megahertz. I believe he's using here the original n, but here the bandwidth would be this value. This value is not 1 megahertz. So now the first choice, which is the non-retain to zero, needs lower bandwidth, which is 625 kilohertz. But the DC component problem here is there. So less bandwidth, but we have DC component. If we use non-retain to zero. If you use Manchester, if you remember, Manchester does not have DC component problem and does not have baseline wandering problem. So, but if you use it, then you use to have you need to increase the bandwidth, which is here calculated as n. Okay, so the trade-off is you want higher bandwidth, but if you want the DC component to be minimized, but the bandwidth is higher. فهون خيارنا اما بنختار non retain to zero وبنتحمل الدي سي كومبوننت او بنختار المانشستر وبالتالي بس الباندوث راح تكون اعلى في الحاله. طيب الاكزامبل اللي هذا اكزامبل بورجينا الانكودينج ل 10 بي 10 بي 8 بي 10 بي 8 بي 10 بي يعني كل 8 بت عم نرسل قاعدين 10 بت. براكتيكالي اي بي ام عملت هذا الانكودر. الانكودر هذا بيقدروا يحطوا يعني 1 انكودر 1 كومبوننتس، لكن قسموه ل 2 كومبوننتس. اول 5 بتس من ال 8 بت، احنا عندنا 8 بت، ف 5 بت حطوهم في انكودر لحال و3 بت حطوهم على انكودر ثاني. اوكي، وبعدين they join them here عملوا concatenation. فعندنا 8 bits coming for example 1 1 1 1 0 0 0 0. للاسف القلم مش كثير دقيق لما بكتب، فعشان السرعه كل هذا 3 بت حولهم ل 4 بت، فصار عندي 4 هون، و5 بت اللي هون حولهم ل 6 بت، ف4 زائد 6 طلع لي 10 بت ستريم، واحنا هذا اللي بدنا اياه، كل 8 بت يطلع 10 بت. الان في هون disparity control. هذا disparity control شو وظيفته؟ وظيفته يشوف اذا في يشوف الونز والزيروز في كل كود بيطلع منهم، فاذا شاف دائما بيحسب الفرق بين عدد الونز وعدد الزيروز، فبحيث يكون العدد هذا ما يزيد عن ناقص 2 او زائد 2 سواء كان في الحسابات. يعني الفرق بين الزيروز والونز ما يزيد عن 2. فاذا شاف انه في كود في زيروز كثير او الفرق صار بيناتهم زائد 2، فبيختار كود بيعمل له كومبلمنت بحيث يظل دائما الفرق محصور بين الزائد 2 والناقص 2. في شيء بيسموه running disparity. الحقيقه running disparity هذا كنترولر بيعمل running disparity وبظل دائما يوازن بين عدد الزيروز، الفرق بين عدد الزيروز والونز الموجودين حتى يصير في بالانس للدي سي كومبوننت. هذا مشروع الحقيقه في اماكن اخرى مش في كتابكم هون ولا مكتوب في ريفرنسز ثانيه. الان زي ما انتم شايفين هون الكود هو انا عندي 2 to the power 10 كود اللي هو 1024 كود. بختار انا بحاجه فقط الى 2 to the power 8 اللي هو 256 كودز out of 1024 كودز. ففي عندي لسه زياده بالكودز 768 ممكن يستخدموا هذول redundant code can be used for disparity checking و for error detection و for controlling signal. فهذا كل بدي اياكم بس تعرفوا عن هذا الاكزامبل او هذا الانكودر. طيب هيك بنكون انهينا التوبيك الرئيسي او اول توبيك في هذا الشابتر اللي هو ديجيتال تو ديجيتال كونفرجن. شو كنا نعمل؟ كنا ناخذ ديجيتال داتا ونحولها الى ديجيتال سيجنال عن طريق استخدام انكودر نون ريتين تو زيرو انكودر او ريتين تو زيرو انكودر او مانشستر انكودر او الفايف او الام بي ان بي اللي نسميه بلوك انكودنج سكيمز اند سو اون. الان ننتقل للمحاضره اللي هي انالوج تو ديجيتال كونفرجن. خليني اوقف هون عشان الفايلز ما يكونوا كبيرين على كبير، حجمه كبير، ولما تنزلوه ونعمل محاضره ثانيه نبلش فيها من سلايد 47 اللي بنحكي فيها عن انالوج تو ديجيتال كونفرجن. بدنا نحول انالوج داتا لديجيتال داتا، وهي بدي اياكم تركزوا معي اكثر.